Section 1 Introduction. In this paper, we introduce a new concept called FastBERT, which is a variant of the BERT architecture. The main idea behind FastBERT is to replace the feedforward layers, which contain most of the parameters in large language models, with fast feedforward networks. This is done to optimize the computation process, as not all neurons need to be active for every input during the inference time. FastBERT performs just as well as other BERT-like models of similar size and training procedures. However, the intermediate layers of FastBERT are designed to be exponentially faster. To explain this, let's consider two types of networks, a feedforward network, FF, and a fast feedforward network, FFF, both with n neurons. The time it takes to pass through the FFF is proportional to the logarithm base 2 of n, while for the FF, it's proportional to n. This speed difference is due to the way FFFs organize their neurons into a balanced binary tree and only execute one branch of the tree based on the input. Inference in an FFF is like performing a conditional matrix multiplication, CMM, where the rows of the input interact with the columns of neural weights one at a time. The specific weight column to proceed with is chosen based on the output of the previous operation. This means that all neurons are used only by some inputs and no input needs more than a few neurons to be processed by the network. This is different from the traditional feedforward networks that use dense matrix multiplication, DMM, which computes the interactions of all rows with all columns. Unfortunately, there is no efficient implementation of CMM in any popular deep learning framework. Therefore, we provide a set of CPU implementations based on pointer-batched matrix multiplication routines of the BLAS library. We also compare CPU and GPU implementations at various levels of optimization and note that while there is already significant acceleration, there is potential for more. We also discuss the role of attention in speeding up the execution of the attention mechanism. For a BERT base-sized model with the usual pre-training context size of 128, the per-token inference cost of its attention to all other tokens is only slightly more than the cost of a 128-neuron feedforward network inference. Therefore, we leave the attention layers untouched and focus solely on the intermediate layers hosting the feedforward networks. In terms of comparison, BERT-based feedforward networks consist of 3072 neurons. This is not close to any power of 2, so in the design of FastBERT, we round this number to 4095, the number of nodes in a balanced binary tree of maximum depth 11. Despite this, FastBERT uses only 0.04% of the 3072 BERT-based neurons for inference. However, FastBERT itself consists of 4095 neurons, and so uses 0.03% of its neurons for inference. You might wonder why we only achieve a 78x speedup and not a 341x speedup. The reason is that dense matrix multiplication is the most optimized mathematical operation in computing history. Despite not needing new hardware, we still have to rely on combining high-level linear algebraic routines to implement CMM, which reduces the speedup. We also share the weights of our best model for reproducibility. While we do not provide an efficient PyTorch or TensorFlow implementation of CMM, the fact that only 12 neurons are used in the inference of FastBERT can be verified simply by masking out the output of all but the chosen neurons. In conclusion, we present FastBERT, a BERT-like model that has 4095 neurons but selectively uses only 12, 0.03%, for inference. We find that it performs on par with its BERT peers and provides a 78x speedup over the natively optimized dense matrix multiplication. Through FastBERT and the already considerable speedups by simple FFF implementations, we demonstrate the considerable potential of conditional neural execution and language modeling. Section Summary. In this section, the authors introduce FastBERT, a variant of the BERT architecture that replaces feedforward layers with fast feedforward networks. FastBERT performs on par with other BERT-like models in terms of downstream performance, but its intermediate layers are exponentially faster due to the use of conditional matrix multiplication, CMM. The authors provide CPU implementations of CMM and report a 78x speedup compared to dense matrix multiplication. FastBERT demonstrates the potential of conditional neural execution in language modeling. Section 2 Model. We begin by discussing our model, which is based on the crammed BERT architecture. We've made a few changes to the original design, particularly in the intermediate layers. Instead of using the standard feedforward networks in these layers, we've replaced them with faster versions. We've also simplified the model in a few ways. First, we've removed any differences between leaf and non-leaf nodes. This means we use the same activation function for all nodes. All nodes have output weights, and we've removed all output biases. Second, we've set the leaf size to 1. Third, we've allowed for multiple fast feedforward networks to work together to compute the intermediate layer outputs. We do this by adding up the outputs of each network and using the total as the output for the intermediate layer. We've named our model FastBERT, and we add a suffix to indicate the number of trees and their depth. For example, a model with k-trees of depth d+1 would be called FastBERT kxd. A model with a traditional feedforward layer of width 3072 is a special case of FastBERT, called FastBERT-3072 by 0. When it comes to training, we follow the same procedure as crammed BERT. We disable dropout in pre-training and use a one-cycle triangular learning rate schedule. We train each model for 1 day on a single A6000 GPU, except for our final model, FastBERT-1 by 11 long, which we train for twice as long for better performance. We fine-tune all FastBERT models for various tasks from the GLUE benchmark. We've found that FastBERT models fine-tuned for the COLA task need more training, so we extend the number of epochs to 15. This doesn't improve the performance of the baseline crammed BERT models, but it does significantly improve the performance of FastBERTs. Our results show that FastBERT models trained for 1 day on a single A6000 GPU retain at least 96.0% of the predictive performance of the original BERT base model. However, performance decreases as the depth of the fast feedforward networks increases. This decrease is mostly due to the COLA task. If we ignore this task, all FastBERT models preserve at least 98.6% of the predictive performance. Our best model, FastBERT-1 by 11 long, performs as well as the original BERT base model while using only 0.3% of its own neurons, which is just 0.4% of BERT base neurons. We've made the weights of this model public. In the next section, we discuss how to take advantage of the fact that only a few neurons are needed per inference. Fast feedforward networks have the potential to greatly speed up large language models. For example, GPT-3, a large language model known for its plausible outputs, could be replaced with a fast feedforward network of maximum depth 15. This would use only 16 neurons for inference, which is about 0.03% of GPT-3's neurons. The key to this speedup is the operation of conditional matrix multiplication. We plan to focus our future efforts on implementing this operation efficiently. Section Summary. The authors propose a modified version of the crammed BERT architecture called FastBERT, where the feedforward networks in the intermediate layers are replaced with fast feedforward networks. They make simplifying changes to the original fast feedforward networks and allow for multiple trees to jointly compute the intermediate layer outputs. The FastBERT models trained for 1 day on a single GPU retain at least 96.0% of the predictive performance of the original BERT base model, with the best model performing on par with BERT base while using only 0.3% of its own neurons. This suggests that FastBERT has the potential for significant acceleration in large language models. Section 3.1 Algorithm. In this section, we'll discuss an algorithm for FFF inference, its compatibility with existing processes and hardware, and its performance. The algorithm we're discussing is a recursive one, and we've provided pseudocode for it. It's based on the CMM and the consecutive inference for FFFs, with some modifications. Here, B stands for the batch size, H is the width of the layer input, and 2 to the power of D-1 is the total number of neurons. M_*K and M_L* represent the KTH column and LTH row of M, respectively. The result of the comparison in CMM is assumed to be either 0 or 1. You might wonder if the use of CMM makes FFFs incompatible with existing processes and hardware used for dense matrix multiplication and deep learning. The answer is no, although it does add some complexity. Single-threaded CPU DMM, which is part of feedforward inference, relies on sequential execution of multiplication and accumulation instructions. CPUs, especially edge CPUs, can benefit from replacing DMM with CMM, as seen in FastBERT, because it requires fewer executions of these instructions. Despite the use of conditionality, which is often associated with branching in CPU code, the neural branching, seen in CMM, only adds a memory offset to the relevant pointers. This means that instruction branch prediction is not needed for CMM conditionality. To speed up access to weights, the CPU might need to be hinted to load only relevant columns of the weight matrix, one at a time. Since CMM continues to perform row-column dot products, vector single instruction multiple data, SIMD, parallel processing remains a viable option for speeding up device-specific inference implementations. The GPU DMM computation, which is implicitly multi-threaded, makes extensive use of the single instruction multiple threads, SIMT, approach by executing the same instructions in each thread, just on different parts of the matrices. This also applies to CMM, as the conditionality represented by proceeding to different columns of the weight matrices only affects the offset to the memory used, not the number of times the instructions are executed. However, efficient DMM implementations distribute the matrix multiplication workload in a way that maximizes the use of distributed cache, limiting accesses to the slower global device memory. To reach its full potential compared to the DMM baseline, any efficient implementation of CMM has to manage its caching optimally for tree traversal, not patched dense matrix multiplication. This can be done by always preloading the weights of the relevant subtrees or by using DMM patching strategies but discarding intermediate results where not needed. However, optimizing these without detailed knowledge of the target device can be challenging. We also compared the speed of several available FFF inference implementations. For CPU inference, we used the math kernel library available as part of the Intel 1 API. We constructed 3 levels of implementation using different routines and extensions. For GPU implementations, we used either PyTorch kernels or custom CUDA kernels. We used a native fused implementation, a BMM implementation, and a naive CUDA implementation. For CPU inference, we performed 250 forward passes per entry on Intel Core i7-6700HQ CPUs under Intel MKL version 2023.2.0, using 64-bit variants of all routines. We reported the average time taken by single inference, noting that the standard deviation was always less than 2% of the mean. For GPU inference, we performed 1,000 forward passes per entry on NVIDIA RTX A6000 GPUs under CUDA version 1.1.7 and PyTorch 2.0.1. We measured the GPU time and reported the average time taken, with the standard deviation again well under 2% of the mean in all cases. We used a batch size of 128 × 128 and a hidden dimension of 768. Section Summary. The algorithm for FFF inference is provided, along with modifications for CMM. The use of CMM does not make FFFs incompatible with existing processes and hardware for dense matrix multiplication and deep learning, although it may increase caching complexity. Single-threaded CPU DMM benefits from the replacement of DMM with CMM, as fewer executions of per-element MAC instructions are needed. Efficient implementations of CMM need to manage caching optimally for tree traversal, and not patched dense matrix multiplication. Several FFF inference implementations are compared for speed, including CPU and GPU implementations using different levels of BLAS routines and custom CUDA kernels. Section. Results. We're going to discuss the results of a performance comparison between feedforward and fast feedforward layers as used in BERT base and FastBERT -1/11. This comparison is presented in a table, where each column shows the speed improvements when using the same basic linear algebra operations in both feedforward and fast feedforward implementations. However, there are 2 missing entries in the table for the BLAS Level 3 and native fused implementations of fast feedforward layers, as these are currently not available. All the speed improvements reported in the table are based on fair comparisons. This means that both the feedforward and fast feedforward implementations use the exact same basic linear algebra operations. You might also be interested in knowing how the best current implementations of fast feedforward layers compare to the best implementations of feedforward layers, even if the latter use operations that are not available for the former. When it comes to CPU performance, the Level 1 and Level 2 implementations of fast feedforward layers perform inference 48 times and 78 times faster than the fastest feedforward layer implementation, respectively. As for GPU performance, the PyTorch BMM implementation of fast feedforward layers is 3.15 times faster than the fastest feedforward layer implementation, Looking ahead, the groundwork for efficient implementation of fast feedforward inference has already been laid within the PyTorch library. If hybrid vector-level sparse tensors were fully supported for both singular and batched matrix multiplication, it would be enough to implement CMM and fast feedforward inference. Moreover, a native implementation of CMM as part of device-specific Intel MKL, NVIDIA Cubless code could potentially deliver a 341-fold speed improvement.